All right, so now I want to talk about non-uniform circular motion. We spent quite a bit of time on circular motion, talking about the acceleration vector and the velocity vectors and the position vectors, and we came up with an expression for the magnitude of the acceleration that was a equals v squared over r. But now what if we're moving in a circle, but it's non-uniform motion? So for starters, what if we're moving in some circle and our velocity is changing. So it's not a constant velocity. So we're at some point on the circle, maybe right here. So we can mark that. And my velocity vector, stick with the blue, my velocity vector is tangent, just like it always has been. But I'm slowing down. I'm still moving in a circle. The radius of my circle is not changing, but I'm slowing down. So at this particular point right here, I have some acceleration that is opposite the direction of my velocity. So I have some piece of acceleration, let's see, that is going in the opposite direction, in exactly the opposite direction. Now, this is only true when you have this non-uniform circular motion when the speed is changing, when the magnitude of your velocity is changing. But we saw in the acceleration vector video in uniform circular motion that since my velocity vector is changing its direction, there has to be some piece of acceleration. We can see from this, there has to be some piece of acceleration that's responsible for that change in direction. This piece right here is exactly parallel, just in the opposite direction. So if this was the only part of my acceleration vector, I would just continue on a straight line this way and I would just be getting slower and slower. But I still have to be curving along this circle. And so we still have part of an acceleration vector that is pointing in this direction toward the middle of the circle. So these are called we have two perpendicular components of acceleration. So if we're slowing down around a circle, if our speed is decreasing, or increasing for that matter, but in this example, increasing, we have two pieces of the acceleration vector. This piece that's responsible for changing the magnitude of our velocity is called the tangential component of acceleration. The tangential component of acceleration. And this piece that's responsible for changing the direction of our velocity is called the radial component of acceleration, because that is still pointing in the direction of the radius. And so for non-uniform circular motion, we can write our full acceleration vector like this. The acceleration vector is the sum of the tangential component vector and the radial component vector. So it's these two components. Instead of an I hat and a j hat direction, like we describe vectors in the plane or vectors in space or something like that, we have these components, one tangent to the circle and one pointing in the direction along the radius of the circle. And now if we were speeding up, so if we were going along the circle speeding up, then our acceleration vector would be pointing in the same direction as our velocity vector. The tangential component of the acceleration vector would be pointing in that same direction. So for this particular case, with this component pointing opposite velocity, we're just slowing down around the circle. Now, this is pretty much as far as it'll go in a standard calculus-based Physics 1 course. You could also have cases where you're traveling around a circle and instead of your velocity changing, so you're traveling around the circle, but maybe your radius is changing. So maybe you're traveling around and you're getting bigger and bigger in some spiral, or maybe you're getting smaller and smaller. And not much changes there either. You still have a tangential and a radial component of acceleration. And in both cases where your velocity is changing speed or your circle's radius is changing, the magnitude is still the same. We still get the magnitude, a equals v squared over r. So it doesn't matter what kind of circle you're moving in, that's always going to be the magnitude of your acceleration. Now, you probably won't talk about solving for these components in a normal physics class, but there is a way there is a way to solve for these components. And that's really, you'll take a dive into that in a standard, in a normal Calc 3 course. It gets pretty involved to calculate these components of acceleration, and what it involves the unit tangent vector, and the principal unit normal vector. And so I want to keep this playlist strictly with the content of your normal physics course, so I won't go into that. But if you are interested in seeing these calculations for these components of acceleration in non-uniform circular motion, you can take a look, and this is the topics to look for. The chapter that includes these topics generally includes calculating these components. And also, it goes deeper than that. It's not just a circle. You can calculate the components of acceleration along any given curve. So that's a deeper dive, but that's more Calculus 3 than it is physics. Most of the problems you'll see in a normal Physics 1 class will concern just the uniform circular motion.